Hello friends, welcome to the last lecture of strength of material. Yes, this is the last lecture of strength of material, my friends. And as promised, I have covered the entire syllabus of strength of material from the very basic, my friend. If you watch all my videos of strength of material from lecture 1 till now, I have covered the entire syllabus of strength of material in a very detailed manner. I got less time, but still I tried to cover as much syllabus as possible. I tried to solve as many problems as possible, my friends. So I have completed my promise. It is up to you how you can support me in this journey, my friend. So we have been posting live online lectures of all the subjects of mechanical engineering. So if you are a mechanical engineer preparing for any competitive exam, then my friend, what you have to do, you have to first go and subscribe this channel. Yes, go and subscribe this channel right now, and don't forget to press the bell icon to get all the notifications. Then my friend, what you have to do, hit the like button of this video, my friend. Hit the like button. Remember, my friend, this is an online lecture and the like button is your attendance. So you have to mark your attendance by hitting the like button. And then my friend, in order to support us, you have to share this video with all your friends. You can post the link of this video on your Facebook status. You can post this link of the video on to your WhatsApp groups. You can post it on every social media platform as possible, and we have to reach to a lot of students, my friend. These videos are completely free of cost, my friends. Okay, so in order to be successful, in order to get fruits of our labor, we need these videos to reach to as many students as possible. इस जर्नी में हमको आपका साथ चाहिए. आप इस वीडियो को ज्यादा से ज्यादा शेयर करेंगे, ज्यादा से ज्यादा स्टूडेंट्स इन वीडियोस को देखेंगे, तभी हमको लगेगा कि हमारी जो मेहनत है वो सफल हुई है. So my friends, in order to make this labor, in order to make these efforts successful, please support us by sharing the link of these videos to all your friends. जितने ज्यादा स्टूडेंट्स इन वीडियोस को देखेंगे, हमें ऐसा लगेगा कि उतना ज्यादा हमारा ये जो लेबर है, हमारा ये जो एफर्ट है, सक्सेसफुल हुआ है. सो प्लीज माय फ्रेंड्स, डोंट फॉरगेट to share these videos. Whatever video you are watching, there are online lectures of all different types of subjects in Hindi, in English. There is a separate batch for SSC, JE and AE. So please share all these videos with all your friends. Tell your friends about this amazing YouTube channel where top educators of India are taking online lectures, my friend, completely free of cost. Yes, we are not asking you to pay anything. We are posting these videos completely free of cost. So all you need to do to support us is to share these videos, my friends. Okay, so if you have still not liked this video, I would like you to hit the like button right now, my friend. Okay, and today's topic, the last topic of strength of material, is columns. So let's start with the journey to columns. Let's start with today's topic, which is columns. Now, what are columns, my friend? Columns are structural members which are designed to support axial compressive load. Okay, you can see columns in your houses also. The structure of your house is supported on vertical members. Okay, so these vertical members are subjected to axial compressive load. Okay, they are acting along the axial direction and they are particularly compressive load. Okay, so columns are structural members which are designed to support axial compressive load. Okay, now my friend, let's say we have a column like this. Let's say we have a column like this which is subjected to axial compressive load. Okay, let's say we are applying an axial compressive load. Okay, now if you keep on increasing the load, what will happen? If you keep on increasing the load, if you start increasing the load, there will be a point when this column will break, right? There will be a point when this column will break. This type of failure in compression is known as crushing. Okay, this type of failure is known as crushing. Now my friend, this column is known as a short column. this column is known as a short column. Why, my friend? Because the length of this column compared to cross sectional area is not that long. It is longer than the cross section, but the length is not that much, so it is known as a short column, and it fails under crushing. It fails due to crushing. This failure is known as crushing. It is failing under crushing. If you apply the compressive load, it will break under compression, and this failure is known as crushing. So short columns fail due to crushing. Okay. Now my friend, let's say I am increasing the load, the length of this column. Okay. So let's say this is the column and this is also subjected to an axial compressive load. Okay. So if you keep on increasing the load on this column, look at this length, it is very large compared to cross section. So if you keep on increasing the load on this column, what is going to happen? Let me show you using an example, a real life example. This is a long column, my friend. It is a steel ruler and it is a long column. So if you keep on increasing the load on this, what will happen, my friend? Can you see? Can you see what is happening, my friend? Can you see? It is deflected in lateral direction, right? It is deflected in lateral direction, a sharp deflection. You can see a sharp deflection. You can see a sharp bending. Okay, you can see a sharp bending. This is known as buckling, my friend. This is known as buckling. So if you keep on increasing the load on a long column, what will happen to the column, my friend? The column will buckle. Okay, you will see a sharp bending. So this is known as buckling. So long column fails under buckling. If it is buckled, then for us it is failed. So long column fails under buckling, my friend. So do you understand what is the difference between a short column and a long column? If it is a short column, let's say this column, let's say this is a body, it is a short column. So if you apply load, what will happen? It will not buckle. After some time it will break. So that failure is known as crushing. But if the length is too much compared to cross section, look at this cross section, very small cross section and very large length. So if you apply compressive load on this type of column, what will happen, my friend? It will not break. Before breaking, it will buckle. And if it buckles like this, means it has failed. So long columns fail under buckling. Okay. Now, in this chapter, what is our objective? In this chapter, our objective is to find the load at which the column buckles. So this load is known as critical load of buckling. This PCR, it is known as critical load of buckling, means the load at which column buckles. Okay, so if it is short column, no problem, because short column there will be no buckling. But if it is a long column, then there will be buckling at some point. So we have to find the load at which the column buckles, so that the actual load will always be less than this load. Okay, the safe load will always be less than this load. What will be the safe load, my friend? What will be the safe load? The safe load should be equal to P critical divided by factor of safety. This is the safe load. Let's say your P critical is 100 Newton. Okay, for example, let's say P critical is 100 Newton. So you should never apply 100 Newton. The load should always be less than 100 Newton, because if the load reaches 100 Newton, your column will buckle. Okay, so your safe load should be less than 100. So what we will do? We will divide 100 by some factor. Let's say your factor of safety is 2. Let's say your factor of safety is 2. So what will be the safe load, my friend? 100 by 2 means 50 Newton. So you will only apply 50 Newton. Okay, you will be safe. Okay, you will not take any risk. You can apply up to 100, means you can go up to 90, 99.9, you can go up to that, but you don't want to take any risk. So what you do, you use some factor of safety. So your maximum applicable load, your safe load is only 50 Newton. Okay, you will not cross 50 Newton. The maximum limit is 100 Newton. but you are only applying 50 Newton, so you are safe, my friend. Okay, so our objective is to find this critical load of buckling. So in this chapter we will see how the critical load of buckling is calculated. Critical load of buckling means the load at which the column buckles. And what is buckling? I showed you. What is buckling? It is a sharp bending. It is a sharp bending like this. Okay, this is known as buckling. Okay, so if the length of the column is very high compared to cross section, then the column buckles under compressive load. The column buckles, and we have to avoid this failure. We have to avoid buckling. So we need to find the load at which the column buckles, my friend. Okay, all right, my friend. Now, in order to calculate critical load of buckling, there are different theories. The actual load cannot be calculated accurately. The actual load cannot be calculated accurately. So we assume a lot of things, we apply a lot of theories. So there are different theories, okay? But in our syllabus, we only need to study one theory, which is known as Euler's theory, okay? In our syllabus, we only need to deal with one theory, which is known as Euler's theory. Okay, so in order to calculate the critical load of buckling, we will apply Euler's theory. Okay, so what is Euler's theory, my friend? There are some basic assumptions to Euler's theory, and based on this assumption, an equation is derived to calculate the critical load of buckling. Okay, so let's first understand the assumptions, and then we will see what is the equation derived from Euler's theory of buckling. Okay, if you are still not like this video, my friend, if you are online and if you are still not like this video, this is not fair to me, this is not fair to my efforts. So please hit the like button, mark your attendance right now, hit the like button, my friend, and don't forget to share this video with all your friends. Remember, I have been telling this since day one, sharing is caring, my friend. If you care for your friends, if you care for students who cannot afford to subscribe online classes, who cannot pay for online classes, this is a completely free of cost lecture. So please share this video to all your friends. Maybe someone needs these lectures. Okay, so sharing is caring, my friend. Keep sharing. Okay, so what are the assumptions of Euler's theory? Let's talk about the assumptions. It is important to understand the assumptions. It is important to understand the assumptions so that we will know in which case this equation is valid, in which case this equation is not valid. Okay, so for that we need to understand the assumptions. So what are the assumptions, my friend? The first and a very important assumption is column is initially straight. Column is initially straight. Okay, the axis of the column is a straight line. Second assumption, my friend, is load is axial and there is no eccentricity. Load is axial and there is no eccentricity. Now what does it mean, my friend? Let's say this is the column. Okay, we are assuming that it is straight. Okay, let's say this is the centroidal axis. Okay, it is passing through the centroid of the cross section. This is the centroid of the cross section, center of the cross section. Now our assumption is that the load is acting at this point. Okay, the load is axial. First of all, the load is axial and it is acting at the centroid. Okay, the load is not like this. The load is not like this. Okay, we are assuming that the load is not acting like this. It is axial, so it is acting like this. Okay, this is axial load. Okay, and it is passing through the centroid, means there is no eccentricity. If it is acting like this, that means there is some eccentricity. Okay, this is the centroid and this is the load, so there is some eccentricity. Okay, there is some eccentricity. So in this case, what will happen, my friend? This load will apply some moment also. There will be a couple also. Okay, but what we are assuming that there is no eccentricity. There is no eccentricity. So the load is exactly acting at the centroid. So do you understand the meaning of this assumption? This is a very important assumption in Euler's theory, my friend. Okay. Now, my friend, next assumption is, and this is a very, very important assumption, We will talk about this later. Okay, we will talk about this later. There is a concept related to this assumption. This assumption is that the stress is within proportional limit. A very important assumption, and we use this assumption in every chapter. Okay, in bending stresses, torsional stresses, in every chapter we have used this assumption to derive the equation. So all the equation that we see, sigma equals to my by I, tau equals to tr by j, all these equations are derived using this assumption. Stress is within proportional limit. And why do we use this assumption? Why do we make this assumption? So that we can use Hooke's law. So that we can use Hooke's law. Hooke's law is valid up to what point? Proportional limit. Okay. So we are using this assumption that stresses are within proportional limit, so that we can use Hooke's law. All these equations are derived using the Hooke's law. Even the Euler's theory equation derived by Euler's theory is also based on the assumption that stress is within proportional limit, means we are using Hooke's law to derive the equation. So whatever equation we derive, it is only valid up to proportional limit. This equation, all these equations are only valid up to proportional limit, but practically proportional limit and yield point are very close. So we can also say that it is valid up to yield point. Okay, some of you might get confused that we use it up to yield point. Sir is saying proportional limit, so don't get confused. Proportional limit and yield point are very close to each other, so we almost consider them to be a single point. Okay, so we can also say that stresses are within yield point. Okay, instead of proportional limit, you can also call it yield point, because they are very close to each other. So these are the assumptions that we make in Euler's theory. Do you understand them? Apart from this, there are some other assumptions also. Cross-sectional area is constant, material is homogeneous and isotropic. All those assumptions are basic assumptions. They are used in every chapter, but in this particular chapter, these are special assumptions. Okay, column is initially straight, load is axial, it is not acting like this, it is not inclined, it is axial, and there is no eccentricity, means the load is passing through the centroid, and the stress is within proportional limit, my friend. Okay, now based on this assumption, we derive Euler's theory, we derive the equation of critical load. So what is the equation of critical load according to Euler's theory? It is given by P critical equals to pi square E I minimum divided by LE square, where P critical is what? It is known as Euler's critical load of buckling. We are using Euler's theory, so we are saying it Euler's critical load of buckling. Okay, we will call it Euler's critical load of buckling. E is what? It is a material property. E is a material property known as Young's modulus. For steel, what is the value of Young's modulus? For steel, we have been repeatedly using the value of E. 200 gigapascal, my friend. For steel, Young's modulus is 200 gigapascal. Now, my friend, a very important thing to understand. I minimum. A very important thing to understand, I minimum. So what is I minimum, my friend? Let's understand that. Okay, let's understand what is I minimum. Okay, let's understand what is I minimum. So let's say, my friend, we have a rectangular section. Okay, let's say we have a rectangular section, and this is width, this is height, this is x-axis, this is y-axis. Okay, x-axis and y-axis. Okay, this is x-axis, this is y-axis. My friend, we have two moment of inertia. Ix will be bh cube by 12. Okay, and Iy will be hb cube by 12. Out of these two, one will be maximum and one will be minimum moment of inertia. For this rectangle, out of Ix and Iy, one is maximum moment of inertia, one is minimum moment of inertia. Now here we need to put minimum moment of inertia. So which one will be minimum moment of inertia, my friend? Let's say this is 50. Okay, let's say this is 50 and let's say this is 100. So this will be 50 into 100 cube by 12, and this will be 100 into 50 cube by 12. So which one is minimum, my friend? This one is minimum. In my example, this was is minimum, I minimum, right? So we have to put I minimum, means it is minimum of, in most of the cross sections, it is minimum of Ix and Iy. For this example, Iy is minimum. In some cases, Ix might be minimum. So I minimum is minimum of Ix and Iy, my friend. Now, what is the meaning of this? Let's understand. Let's understand what is the meaning of this. Why I minimum? Let's understand this. Let's say this is a column. Okay, let's say this is a column. Now, my friend, look at this cross section. It is like this, right? Width is less and height is more. Okay, width is less. It is like this. Okay, so there are two axes, my friend. One is this axis and one is this axis. Okay, there is one axis like this. This is the x-axis. Okay, this is the x-axis like this, and this is the y-axis. Okay, this is the y-axis. Okay, this is the vertical axis, this is the horizontal axis. Now, my friend, if you apply a compressive load, it can bend about x-axis and it can bend about y-axis. This is bending about y-axis. Okay, this is the y-axis. So it might bend like this. It might also bend like this. Okay, it might also bend like this. Okay, it can bend like this. It can bend like this. Okay, it can bend in this direction. It can bend in this direction. Okay, like this and like this. So about which axis it will bend? About which axis it will bend, my friend? Moment of inertia is resistance to bending. Moment of inertia is resistance to bending. So if resistance is more about x-axis, if resistance is more about x-axis, then it will bend about y-axis. And if resistance is more about y-axis, it will bend about x-axis. Okay, so minimum moment of inertia means minimum resistance. Okay, minimum moment of inertia means minimum resistance. So if the resistance is minimum about x-axis, it will bend about x-axis. If the resistance is minimum about y, it will bend about y. Look at this cross section. About which axis resistance is minimum? This axis or this axis? Look at this. About which axis resistance is minimum? Y-axis, Iy. This is the axis about which resistance is minimum. This is the axis about which I is minimum. So it will bend about this axis. Okay, it will bend about this axis, means it will bend like this. Okay, about this axis. So if you apply the load, see, it always bends like this. It never bends like this. Why? Because the resistance is more about this axis. Okay, so it will first bend about this axis. Okay, so this is I minimum. Do you understand this? Do you understand this? What is I minimum? Minimum of Ix and Iy. Why we are using it? Because if Ix is minimum, it is going to bend about x-axis. If Iy is minimum, it is going to bend about y-axis. Do you understand this? Alright, my friend. For circular section, Ix and Iy both are equal. So it can buckle about x, it can buckle about y. Doesn't matter. Okay. Now, my friend, a very important point, LE. Very, very important point, LE, which is known as effective length of column. What is LE, my friend? It is known as effective length of column. Okay. Now I want you to note this equation down. First you note this equation down, and then we will talk about effective length of column, because this is the most important parameter in this equation. In this equation, this is the most important parameter. In order to use this equation, you have to understand this parameter LE. So note this down, and then we will see what is LE exactly, what is effective length of column. Okay, so note this down, my friend, note this down. P critical equals to pi square EI by LE square. So this is Euler's theory. Okay, this is Euler's theory. Now, my friend, let's understand effective length. Let's understand effective length. So what happens, my friend, when we derive the equation of critical load, when we derive this equation, critical load, we have to assume some end condition of the column. We have to assume end condition. End condition means there must be some support to the column, right? There must be some support to the column. So we have to assume what are the types of supports. Okay, what is the support at one end, what is the support at the other end. Okay, so we assume four types of conditions. We assume four types of condition. Okay, this is effective length. We are talking about effective length, and this is very important. Most of the questions in columns are based on this effective length. Okay, you might get theory question, you might get conceptual question from effective length. So it is very important to understand. Okay, it is very important to understand. So what do we do, my friend? We assume different end condition. Okay, for example, let's say this is the first end condition. Let's say this is the first end condition. Both the ends are hinged. Okay, what is this condition, my friend? Both the ends are hinged. Okay, now don't say that it is a roller support. This is a double roller and it is a guided roller. Guided roller is like a hinge. Okay, guided roller is like a hinge. Okay, so this is like a hinge support. Okay, guided roller. Okay, see about this point, will there be any deflection in this direction? No, right? Will there be any deflection in this direction? No. So this is a hinge support. It is acting like a hinge support. This is a guided roller. Okay, it is guiding this end in a particular direction. Okay, so it is a guided roller. Now, my friend, both these ends are hinged and you are applying a load like this. Okay, in this case, both ends are hinged. Both ends are hinged. Okay, this is one condition. Second condition, one end is free and other end is fixed. Okay, this is the second condition. One end is fixed, other end is free. Okay, this is the second condition. Okay, third condition, both ends are fixed. Both ends are fixed. This is the third condition. Okay, and the fourth condition is one end is hinged. One end is hinged and other end is fixed. Okay, again a double guided roller acts like a hinge. Okay, it acts like a hinge. So in this case, one end hinged, other end fixed. Okay, so do you understand? These are the four conditions. Okay, in first condition both ends are hinged, in second condition one end is fixed, other end is free, in third condition both end is fixed, and in fourth condition one end is hinged and other end is fixed. Okay, now what will happen in all four conditions? Let's understand this. What will happen in all conditions? See, my friend, buckling is nothing but bending. Buckling is nothing but bending, and I told you in case of different types of supports, what are the boundary condition in bending, in deflection of beams? Remember, I explained the boundary condition when there is a roller support, when there is a hinge support, when there is a fixed support. You know how the end condition will be. You know what will be the boundary condition. So in case of hinge, what happens, my friend? In case of hinge, the deflection is zero, right? At this point, deflection will be zero, and we are talking about bending in this direction, not in this direction. Okay, this is vertical bending. This is vertical bending, and in case of column, there is horizontal bending. Okay, so we are talking about horizontal bending. Okay, so here deflection means deflection in x. Okay, so at this end there will be no deflection in x. At this end there will be no deflection in x. Due to hinge there will be no deflection, but there will be slope. At hinge end this will rotate. Okay, due to hinge it will rotate. Hinge support cannot restrict rotation, so there will be rotation but there will be no deflection. So it will bend like this, it will buckle like this. Okay, this will be the shape after buckling. Okay, look at this, there is some slope here, there is some slope here. Okay, but there is no deflection. Here, my friend, this is a free end, so there will be slope, there will also be deflection. There will be slope, there will be also deflection. But at the fixed end, deflection will be 0, and due to fixed end, slope is also 0. So after bending, after buckling, it will look like this. After buckling, it will look like this. Okay, this will be the final shape after buckling. Look at this point, my friend. Look at this point. There is deflection because it is a free end. So there will be deflection and there is slope. But here, my friend, no deflection and no slope. Here, look at this. Slope is 0. It is like a cantilever beam. Can you understand? It is like a cantilever. Okay. Now, my friend, here both ends are fixed. Means no deflection, no slope. It will be like this. It will be like this. After buckling, it will become like this. Okay. See, at both the ends, no deflection, no slope. Here, my friend, one end is hinged, no deflection, but there will be slope, and one end is fixed, no deflection, no slope. So it will look like this. It will look like this. Do you understand, my friend? Do you understand? Here there is some slope because it is a hinge end, but here slope is 0. So look at this. In all four conditions, the shape of the column is different. In all four conditions, the effective length will be different. Okay. So what will be the effective length in this case? In this case, my friend, effective length will be equal to L. In case of both ends hinge, effective length is equal to L. In this case, my friend, effective length is equal to 2L. In this case, my friend, effective length is equals to L by 2. And in this case, one end fixed, other end hinge, effective length is given by L by root 2. So look at this, my friend. In all four conditions, effective length will be different, and if effective length will be different, P critical will be different. What is the equation of P critical, my friend? What was the equation of P critical? P critical equals to pi square EI minimum by LE square, right? So P critical, my friend, is inversely proportional to LE square. So if LE is more, P critical is less. If LE is less, P critical is more. Now, my friend, logically tell me, without looking at this, logically tell me in which case P critical will be less. Means which column will easily buckle, which column will first buckle, which column will buckle first. In all four conditions, logically, just apply common sense and tell me which column will buckle first. In this case, both ends are hinged. In this case, both ends are fixed. In this case, one end is hinged and one end is fixed. So in these three cases, there is some support at one end and other end. But here, one end is free. One end is completely free. So this column will buckle first. This column will buckle first. Means in this case, P critical will be minimum, right? In this case, P critical should be minimum and effective length is maximum. See, in all four cases, which has the maximum effective length? This one, LE equals to 2L. If LE is more, if LE is more, P critical is less. If LE is more, P critical is less. So for this, P critical will be less. This column will buckle first. Which column will buckle last? Which column will buckle last, my friend? If LE is less, P critical will be more. So which column will buckle last, my friend? In all four conditions, which column will buckle last? Look at this. In this case, both the ends are fixed. So this column is going to buckle last. Means P critical will be more for this column. P critical will be more for this column. LE is less for this column. Look at this. This is the minimum LE. L by 2. This is the minimum LE. So for this column, P critical will be maximum. It will buckle last. Okay. So do you understand this? You can use this logic to remember this also. You can use this logic. This is maximum LE, 2L. This is minimum LE, L by 2. So for which column LE will be 2L? If one end is free and other end is fixed. And for which column LE will be L by 2? If both ends are fixed. This will buckle first, this will buckle last. When both ends are hinged, LE is equal to L. Okay, when both ends are hinged, LE will be equal to L. And the fourth condition, one end is, another end fixed, LE equals to L by root 2, my friend. Okay, so you have to remember all these four effective lengths, my friend. You have to remember all these four effective length. Okay, note this down and remember all 4 effective length. Remember the equation of all 4 effective length. So effective length depends upon the end condition, how the column is supported. So we are assuming 4 different types of end condition, 4 different combination of supports, and in each combination there is a different equation of effective length. Okay, so most of the questions are based on effective length. There will be 1 mark question. 1 mark question means they will ask you, if both ends are hinged, P critical is this much. What will happen if both ends are fixed? What will happen to critical load if both ends are fixed? Okay, so you should know the effective length in both the cases, and you can calculate the P critical. Okay, so most of the questions of column are based on effective length of column. 1 mark question, you will see a lot of 1 mark question in different exams, mostly in PSUs, in ESC, there will be lot of 1 mark question. So there you will find 1 or 2 question based on column where they will ask you about effective length. Okay, so this is a very important topic, effective length of column. Okay, now let's solve 1 or 2 problems based on effective critical load of buckling. Okay, based on the equation of critical load, let's solve some problems. Let's solve some numericals. Let's solve numericals directly from gate. Okay, let's solve numericals directly from gate. So the first numerical that I will solve is, first numerical that I am going to solve is from gate 2015. From gate 2015. This question is from gate 2015. A very simple question. A very simple question. What is given in the question? Consider a steel column. Consider a steel column. Young's modulus is given 200 gigapascal. Hinged at both the ends. Hinged at both ends. Okay. Hinged at both the ends. Cross section is given and length is given. Length is 1 meter. Cross section is 10 mm by 20 mm. Okay. And what you need to calculate? Critical load of buckling. Euler's critical load of buckling. Okay. So this is the question. Very easy question. You just have to put the values in the equation, my friend. Okay. So what is the equation, my friend? P critical equals to pi square E I minimum by LE square. Okay. Pi square E I minimum by LE square. Now first of all, tell me what will be the effective length in this case, hinged at both the ends. If it is hinged at both the ends, what will be the effective length, my friend? Tell me what will be the effective length. Tell me. If it is hinged at both the ends, the effective length will be L. So I can write it L. L square. Okay. Now put the values in the equation. So it will be pi square E. It will be 200 gigapascal. So I have to convert it into megapascal. Newton per mm square. You have to put everything in Newton and mm. So Newton per mm square into I minimum. What will be I minimum, my friend? Look at the cross section. It is 10 by 20. 10 mm and 20 mm. So one moment of inertia will be 10 into 20 cube by 12 and one will be 20 into 10 cube by 12. Okay. So which one will be minimum, my friend? It will be 20 into 10 cube by 12 divided by L square. So what is the length? 1 meter, my friend. So I can write it 1000 mm. So 1000 square. So put the values and solve this equation. What you will get, my friend? Very easily you can calculate. What you will get? You will get 3289.86 Newton, my friend. This is the critical load, means at this load the column is going to buckle. If they ask you safe load, if in any question they ask you to calculate safe load, what you need to do? P critical divided by factor of safety. If factor of safety is given in the question and they are asking safe load, what you need to do? First calculate P critical, then P critical divided by factor of safety, my friend. This is the maximum load, but you don't use the maximum load. You don't use the apply the maximum load. You have to remain safe. You have to be safe. So the maximum load should you will apply less load than maximum load. So you will divide this by some factor 1.5, 2, 2.5, 3. So P safe will be P critical by factor of safety. Okay, so this was a very easy question from GATE 2015. In fact, other questions are also like this, very easy, very simple. Let's solve another question, a different type of question. Okay, let's solve a different type of question. So this question is from GATE 2008. This question is from GATE 2008. This next question is a little different and it is from GATE 2008. Okay, so what is the question, my friend? You have a rod. Okay, you have a rod of length L. You have a rod PQ of length L hinged at both the ends. Okay, it is hinged at both the ends. Now don't say that it is a roller support, it is a guided roller. It will act like a hinge support. Okay, now my friend, there is a force F acting and this column is at 45 degree. It is not necessary that column is always in vertical. Okay, the columns are not always vertical. In case of truss, okay, truss members are also subjected to tension and compression. So in case of truss, the members can be inclined. Okay, there will be a member subjected to compression and it is inclined. So this is a case where the column is inclined. Okay, so this particular column is inclined and the load is acting like this, and we need to calculate P critical in terms of F. The answer will be in terms of F. You need to calculate P critical. Now my friend, look at this. Look at this load. What is our assumption in Euler's theory? That the load is axial, right? Look at this load. Is it axial? Is it axial? No, it is not axial. So what we are going to do in this question, we are going to resolve this force into two components. One component will be tangential and one component will be axial, like this. Okay, this will be F cos 45, this will be F sin 45. Now my friend, according to Euler's theory, the buckling will take place only due to F cos 45. We will not consider F sin 45. Okay, buckling will take place only due to F cos 45 according to Euler's theory. So what will be your equation, my friend? P critical equals to, look at the end condition, both are hinged, both the ends are hinged, so it will be L. LE will be L. So pi square EI by L square. And what will be P critical, my friend? Which one will cause the buckling? F cos 45, right? So F cos 45. Sorry, you don't need to calculate the P critical. In this question, you need to calculate F. Sorry. You need to calculate F. So F cos 45 will be equal to pi square EI by L square. And if you calculate F, what you will get? Root 2 pi square EI by L square. So at this value of F, the column will buckle. Okay, at this value of F, the column is going to buckle. So do you understand this question? If the load is inclined, what you have to do? Resolve the force and only consider the axial component. Only consider the axial component. Okay, if the load is inclined, resolve the force and only consider axial component. So if you are learning something new, if you are learning something interesting, please hit the like button, my friend. Hit the like button and don't forget to share this video, my friend. I am telling you, my friend, we are putting a lot of efforts. All of the members of our team are putting a lot of efforts making these videos. Okay, there are amazing videos on our YouTube channel, Unacademy GATE. We are not posting only lectures. We are also posting different types of videos. For example, there is a playlist called Real Life Engineering Application, where you will find videos related to real life application of engineering concept. For example, clutch, how the clutch works, when the clutch fails, how the clutch fails. So you will understand all this using practical example. Okay, in that video you will see practical example of clutch and there will be some animation in that video, so you will be able to understand it better. Okay, so we have all been understanding these lectures, but we never use the real life application. Okay, we never see the real life application, so we are posting real life application videos in that playlist. So go and watch that playlist. Okay, after this lecture ends, go and watch that playlist. So there are a lot of videos. There are videos related to PSU interview, MTech interview. We are sharing our experience of MTech. We are sharing our experience of working in PSUs. So there are a lot of different types of content in our YouTube channel. So go and subscribe the channel if you have not subscribed till now. And my friend, you also have to share these videos. You have to support us, my friend, in this journey. This is your YouTube channel. This is your YouTube channel. Okay, we are all like a family. 51,000 students, 51,000 people. We are all like a huge family, my friend. We have to support each other. So we are supporting you by providing you quality content. You can support us by sharing these videos. Okay, by sharing these videos with all your friends. Okay, thank you very much if you have already shared, my friend. Okay, now my friend, let's move on to the next question. And this another question is from GATE 2019. This question is from GATE 2019. A very interesting question. A very interesting question, my friend. Okay, so let me read the question first. Consider a prismatic straight beam. Okay, consider a prismatic straight beam. Prismatic means cross-sectional area is constant. Cross-sectional area is constant. It is hinged at both the ends. Length is pi meter. The length of this beam is pi meter. Okay. Young's modulus is 200 gigapascal. Young's modulus is 200 gigapascal. Cross section is 6 mm by 6 mm. It is a square section, 6 mm by 6 mm. Okay. Alpha value is given. Alpha is what? Coefficient of thermal expansion. Okay. We have considered this in bars. Thermal stress. So alpha is given 3 into 10 to the power minus 6 per degree Kelvin or per degree centigrade. One and the same thing. Minimum temperature rise. Find the minimum temperature rise. Find minimum temperature rise to cause Euler's buckling. To cause Euler's buckling. So do you understand the question, my friend? Do you understand the question? See, this beam is hinged at both the ends. Let's assume that we are increasing the temperature. Okay, let's assume that we are increasing the temperature. So if you increase the temperature, what is going to happen, my friend? If you increase the temperature, then it will try to expand. If you increase the temperature, it will try to expand, but the supports will not allow this to expand, and the supports will apply some reaction. Let's say this is P, this will also be P, right? If you increase the temperature, the supports will apply a reaction force P and P. You have to find minimum increase in temperature to cause buckling. Do you understand? You have to find minimum increase in temperature to cause buckling. Understand this question, my friend. Understand this question. Understand the question. And then let's understand the solution. So if you increase the temperature, it will try to expand and the supports will apply compressive load like this. Now, my friend, you have to find minimum temperature rise to cause Euler's buckling. So for Euler's buckling, what will be the condition? For Euler's buckling, this P should be equal to or greater than P critical. Okay, it is going to buckle at P critical. So P should either be equal to P critical or greater than P critical. If P is less than P critical, it is not going to buckle. P critical means the load at which buckling happens. So P should be equal to P critical or greater than P critical. It should not be less than P critical. If you want buckling, right? So P should be greater than or equal to P critical. Now, my friend, what will be the value of P? What will be the value of P? I told you to remember the equation of sigma. In this case, when both the ends are fixed and you are increasing the temperature, what was the equation of sigma? I told you to remember it. It is equal to E alpha del T. If you don't remember it, watch the video on thermal stress. I have made a very excellent video on thermal stress. So please watch that lecture. Sigma equals to E alpha del T, but here we don't need sigma, we need load. So what will be the load? Sigma is equal to what? Load upon area. So what will be load? A E alpha del T. So E alpha del T is thermal stress. This is thermal force. Okay, this is thermal force. A E alpha del T. So put the value A E alpha del T should be greater than or equal to P critical. Now what is the equation of P critical according to Euler's theory? What is the equation? Pi square E I minimum by LE square. What is the effective length in this case? Both the ends are hinged. In most of the numericals, both the ends are hinged. So it will be L. LE will be L. Now put the value in this equation. E cancel. Okay. Put the values, other values. What will be alpha area? 6 into 6. What is alpha? 3 into 10 to the power minus 6 into del T. Delta T is required to be calculated. Pi square. What will be I minimum? Cross section is square, 6 by 6. So it will be 6 into 6 cube by 12 divided by L square. What is L, my friend? L is pi meter. So you can write pi into 10 to the power 3 mm. So this is the equation, my friend. In this equation, there is only one unknown, delta T, my friend. Okay. In this equation, there is only one unknown, delta T. And if you calculate delta T, you will get 1 Kelvin or 1 degree centigrade. It is change in temperature. So degree centigrade and Kelvin both will be same. It is change in temperature, T2 minus T1. So it will be same, degree centigrade or Kelvin, it will be same. So this is the minimum temperature. If the temperature is less than 1 Kelvin, if the increase in temperature, change in temperature is less than 1 Kelvin, there will be no buckling. But if you increase the temperature more than 1 Kelvin or equal to 1 Kelvin, then it is going to buckle. This is a very important concept, my friend. This is a very important concept. Okay, remember this. For Euler's buckling, P should be greater than or equal to P critical. Just put the value of P. What is thermal stress? E alpha del T. And stress is load upon area. So what will be thermal load? Thermal stress into area. A E alpha del T. P critical we already know. Pi square EI by L square. So if you solve this equation, you will get the value of delta T. Do you understand it? If you are learning something new, hit the like button, my friend. Hit the like button and share this video with all your friends, my friend. Share this video with all your friends. That is what I need from you. Sorry for that. That is all I need for you. That's all the support I want from you. Okay. So do you understand this? Do you understand this? Note it down. Note it down, my friend. And let's move on to the next topic. The next topic, which is a conceptual topic. A very interesting concept. A very interesting concept we are going to learn. And this next topic is known as limitation of Euler's theory. Limitation of Euler's theory. Okay, let's understand limitations of Euler's theory. My friend, when we derive the equation of P critical in Euler's theory, we make some assumptions. Out of those assumptions, one assumption is that the stress is within proportional limit. So this means that whatever equation we have derived, it is only valid up to proportional limit. After proportional limit, you cannot use this equation. Okay, after the stress crosses proportional limit, this equation will not be valid. So whatever equation we derive, it is only valid. Euler's theory is only valid if sigma critical means at critical load, what will be the stress? So whatever stress you are getting, it should be less than or equal to sigma P, means proportional stress. Okay, stress at proportional limit. Okay, so sigma critical should be less than equal to sigma P. Now my friend, what will be sigma critical? P critical by area. Sigma critical means stress at buckling. So it will be P critical by area, load upon area. and it should be equal to less than equal to sigma p. So if your stress is greater than sigma p, then Euler's theory will not be valid. It should be less than or equal to sigma p. Okay, why? Because we have used Hooke's law. In order to derive Euler's theory, there is Hooke's law involved, and Hooke's law is only valid up to proportional limit. That's why if you want to use the equation of P critical, then sigma critical should be less than equal to sigma P. Now put the value of P critical here. What will you get? Pi square EI minimum by LE square divided by A should be less than equal to sigma P. Now my friend, in this equation, I can write moment of inertia equal to A into K square, where A is the area. What is K, my friend? What is K? K is known as radius of gyration. Now my friend, this concept of radius of gyration, you will understand it in engineering mechanics. You should know about this. Okay, it is related to moment of inertia, but if you don't know, let me explain this very briefly. Okay, I will use a simple explanation to explain the meaning of radius of gyration. Okay, let's say we have an area and we want to calculate moment of inertia. What is moment of inertia? Area into distance square. Second moment of area. Second moment of area. Moment of inertia is what? Second moment of area. Area into distance square. But my friend, the entire area is not at one distance. Every particle of this area is at some different distance. Let's say this particle is at 1 meter. This particle is at 2 meter. This particle is at 3 meter. So every particle is at different distance. So we cannot calculate moment of inertia by area into distance square. The entire area is not at a single distance. But if I assume that the entire area, let's say this area is A. Let's say this area is A. Let's assume that this entire area is like a very thin strip. Very, very thin strip. Then in this case, my friend, this area, all the particles of this area are at the same distance. Right now, practically, different particles are at different distance. But let's assume that the entire area is at same distance. Let's assume that entire area is like a very thin strip. So the entire area is at one distance. Then this distance is known as radius of gyration. So what you are doing, you are assuming that entire area A is at one single distance. All the particles are very close, so they are at same distance K from this axis. Now what will be your moment of inertia? All the particles are at same distance, so it will become area into distance square. I equals to AK square. Okay, I equals to AK square. So do you understand the meaning of radius of gyration? I am assuming entire area is at one distance, then that distance is radius of gyration. Okay, so I can be written as AK square. And what is K minimum? Minimum radius of gyration. Okay, K minimum means minimum radius of gyration. So put I equals to AK square. What you will get? Put I equals to AK square. What you will get, my friend? If you put I equals to AK square in this equation, you will get this. Pi square E AK minimum square divided by A into LE square. Okay, this LE, I have got it here. It should be less than or equal to sigma P. Now, this area and this area will be cancelled. Now, my friend, in this equation, you will see two types of parameters. There are different parameters. You will see two types of parameter. One type of parameter is related to material. So which parameter is related to material? E and sigma P. These two are related to material. And one type of parameter is related to geometry. Which parameter is related to geometry? Length is related to geometry. K is related to geometry. So let's put these values on one side these are related to material, and these two on this other side. I can write it like this. Now, this LE by K minimum, this ratio, my friend, is a very important ratio. It is denoted by lambda and it is known as slenderness ratio. It is known as slenderness ratio. What is slender? What does it mean, slender? Slender means if the length is greater than cross section. Let's say this is a slender member because the length is more than the cross section. It is known as a slender member. Slenderness means how slender it is. Okay, this ratio will tell you how slender your member is. If the length to this ratio K minimum is very high, means it is very slender, and if this ratio is very less, means it is less slender. So this ratio will tell you how slender your column is. Okay, now my friend, if you calculate the value of lambda, then it will be equal to, lambda should be greater than or equal to pi root over E by sigma p. This is the limitation of Euler's theory. Euler's theory is only valid if the slenderness ratio of the column is greater than or equal to this value. This value will depend upon the material of column E and sigma p. These both values are related to material. They depend upon material. Let's say mild steel. Let's say your material is mild steel. So for mild steel, Young's modulus is 200 gigapascal and sigma p is around 250 megapascal. Okay, for mild steel. So for mild steel, lambda should be greater than or equal to, if you put this value and if you calculate it, it will be almost equal to 89. So for mild steel, you can use Euler's theory only if lambda is equal to greater than 89. If it is less than 89, then you cannot use Euler's theory. So do you understand this point? Do you understand this point, my friend? Euler's theory is only applicable if the value of lambda is greater than or equal to this value. What is this value? Pi root over E by sigma p. This depends upon the material. So for different material, this value will be different. So for mild steel, lambda should be greater than or equal to this value, then only Euler's theory will be applicable. Do you understand this? If you understand it, hit the like button right now. Hit the like button right now and memorize this equation. A very important assumption. A very important equation. Euler's theory is only valid if this equation is satisfied. Okay, and also memorize this. What is slenderness ratio? LE by K minimum. Okay. So you will get theory question, conceptual question based on this concept, based on this topic, limitation of Euler's theory. So Euler's theory is not always applicable. It is only applicable if this equation is satisfied. Okay. All right, my friend. Now another very interesting concept in this next topic, we are going to discuss another very interesting topic, very interesting concept, my friend. This next topic is known as kern or core area of column. Kern area of column or core area of column. Okay. Now in order to explain this, I am going to use a very simple example. Okay. What is kern or what is core? If you want to understand it, let's take an example. Let me take an example of a circular column. Okay, let me take an example of a circular column. Okay, the cross section, this is the cross section. Okay, this is the cross section. Okay, cross section means side view. Okay, let's say this is the column. Let's say this is the column. So this view, top view. Okay, I should say top view. This is the top view. Okay, this is the cross section. Okay, circular. So this is a circular column. This is the centroidal axis. Okay, this is the centroid. Let's say it is subjected to, an axial load, but the axial load is not acting at the centroid. Let's say the axial load is eccentric. What is eccentric? Eccentric means the load is not passing through the centroid. Let's say the distance from centroid is E. So what will happen in this problem, my friend? What will happen in this case? If the load is not acting at centroid, what you will do? You will transfer this load at the centroid. So if you transfer this load at the centroid, what you will get? You will get a load P and a moment P into E. Okay, so the load was eccentric, so I transferred the load. So now I am getting a load and a moment. What is this moment, my friend? It is a bending moment. This moment is a bending moment. It will try to bend this body. Okay, now my friend, what will happen in this case? In this case, in the cross section of the column, there will be two stresses. In the cross section, there will be two stresses. There will be a compressive stress. There will be a compressive stress due to this axial load. There will be a compressive stress due to axial load, axial compressive stress. So what will be the value of axial compressive stress? It will be equal to minus P by A. Sigma equals to minus P by A. It will be the axial stress minus P by A. From top to bottom, it will be compressive. Now, my friend, there will be a bending stress also. But the bending stress will not be completely tensile or completely compressive. In half of the cross section, it will be tensile, and in half of the cross section, it will be compressive, right? Neutral axis will be at the center. So in half of the cross section, the stress will be compressive, and in other half, the stress will be tensile. And it will be sigma B. Sigma B means plus minus my by I. My maximum by I here, my maximum by I here. Okay, this will be, let's say, minus my maximum by I, and this will be plus my maximum by I. Okay, now my friend, if you add both these stresses, both are sigma x, so I can directly add these two stresses. Okay, so if you add these two stresses, what will happen? There will be three cases, my friend. If you add these two stresses, there will be three cases. Okay, let me explain all three cases using a diagram. Okay, let me explain all three cases using diagram. Okay, so what will be the case one? What will be the first case? The first case will be when my maximum by I, my maximum by I is less than P by A. Okay, when the magnitude of my maximum by I means maximum bending stress, magnitude of maximum bending stress is less than axial stress, then what will happen? Let's understand it using some example. Okay, let's say the axial stress is 100. So this is minus 100 and this is also minus 100. Okay, for example, let's say axial stress is minus 100 and let's say maximum bending stress is 70. So this is minus 70, this is plus 70. So if you add both these two, what you will get? At top, what you will get? Minus 30. At top you will get minus 30, right? At top you will get minus 30 and at bottom you will get minus 170. Okay, this will be the stress. It is completely compressive. Minus 30 minus 170. Do you understand this? Minus 30 minus 170, completely compressive. Okay. Second case, if my maximum by I, if the magnitude of my maximum by I is equal to magnitude of P by A, in this case what you will get? Let's say this is also plus 100 and minus 100. Okay, this is minus 100 completely, but it is plus 100 here, minus 100 here. So what you will get? At top what you will get? Minus 100 plus 100, 0. At top you will get 0, and at bottom you will get minus 200, compressive. So at top it will be 0, at bottom it will be minus 200, completely compressive. Here also completely compressive, here also completely compressive. Now consider the third case. Consider the third case. My maximum by I is greater than P by A. Consider the third case. My maximum by I is greater than P by A. Then what you will get, my friend? Consider this third case. Let's say this is 150 and this is minus 150. Now what you will get? At top what you will get? 150 minus 100. What you will get? Plus 50. And at bottom minus 250. So your diagram will be something like this. Your diagram will be something like this. At top you are getting some tensile stress. At bottom you are getting some compressive stress. Okay. Now my friend, in some cases of column, we need that the stresses in column should be completely compressive. There are some cases where we want that the stresses in column should be completely compressive. There should be no tensile stress. There should be no tensile stress. There are some design, there are some applications of column where we need that the entire stress in the cross section of column should be compressive. There should be no tensile stress. You don't have to worry about those cases. Okay, the design of column is not in our syllabus, so you don't have to worry about which case we are talking about. Okay, in some cases the stresses in column should be completely compressive. There should be no tensile stress. And if you don't want tensile stress, means this should not happen. This should not happen. This is okay. This is okay. If my maximum by I is less than P by A, okay. Equal to P by A, okay. But it should not be greater than P by A. Okay. So what will be the condition for no tensile stress? What will be the condition for no tensile stress? What will be the condition for no tensile stress? For no tensile stress, my maximum by I should be less than or equal to P by A. Third case should not be happening. My maximum by I should not be greater than P by A. If it is equal to P by A, no problem. Less than P by A, no problem. Now put the values here. Put the values in this equation. What is M? P into E. What will be Y maximum? What will be Y maximum, my friend? What will be Y maximum? D by 2. For circle, D by 2. What will be I? Pi by 64, D to the power 4. Should be less than equal to P by pi by 4, D square. Now solve this entire thing. Pi cancel, P cancel. Solve this entire thing and you will get E equals to, sorry, E should be less than equal to D by 8. Means your eccentricity should be less than D by 8 or equal to D by 8. It should not cross D by 8. Okay. So let's say this is the center. Let's say this is the centroid. Okay. This is the centroid. And let's say this is D by 8. Okay. Let's say this is D by 8. If you draw a circle of radius D by 8, if you draw a circle of radius D by 8, this region, this area is known as kern or core area. What is kern or core area, my friend? If your load is inside this red area, if your load is inside the red zone, there will be no tensile stress because your E will be less than or equal to D by 8. If your load is inside this, your E is either less or equal to D by 8. But if you cross this circle, if your load is acting here, means your eccentricity is greater than D by 8. If you are here, means if your load is acting here or here or here, means your eccentricity is greater than D by 8, and in that case you will get some tensile stress. So do you understand what is kern or core area of column? In some cases we need only compressive strengths. We don't want tensile stresses in cross section of column. In some cases of column design, we don't want any tensile stress in column. So if there is some eccentric load, this is valid for eccentric load. If there is some eccentric load, eccentricity should be less than or equal to some value. Your load should be within some area. Okay, and that area is known as kern area or core area. If your load is inside kern area, no tensile stress. If your load is outside core area, tensile stress. Do you understand this concept? Do you understand this concept? Very good, my friend. Now, my friend, you can also calculate eccentricity for rectangular section. You can also calculate it for rectangular section. For rectangular section, what will be the formula, my friend? This will remain same. So for rectangular section, M will be P into E. What will be Y maximum? For rectangular section, my friend, let's say this is width, this is height. So what will be Y maximum, my friend? H by 2. What will be I? BH cube by 12 should be less than or equal to P by area. What will be area? B into H. So B and B will cancel, P and P will cancel, and if you solve this, you will get this. E should be equal to less than H by 6. So for rectangle, E should be less than or equal to H by 6. For circle, it should be less than or equal to D by 8. You will see a lot of question based on this calculation in your previous year question book. Okay, if you buy any previous year question book for GATE, engineering services, PSU, you will see a lot of question based on this concept. In some case they will give you a circle, in some case they will give you a rectangle, in some case they will give you a hollow circle. So there will be different cross section, but the concept is same. For no tensile stress, My maximum by I means magnitude of bending stress should be less than or equal to magnitude of axial stress, P by A. Put the values here and you will find the value of E. This is so that there is no tensile stress in the cross section of the beam. Do you understand this concept? Hit the like button right now, my friend. And with this topic, I end the strength of material here, my friend. This is the last topic of our syllabus, strength of material, my friend. Okay, so we have completed the entire syllabus of strength of material. You should be congratulate yourself if you have been attending all my lectures from day one. Congratulations to you. Keep up the hard work. Attend all the lectures, my friend, all the lectures. Attend as many lectures as you can and complete the entire syllabus of GATE, engineering services, whatever exam you are preparing for. Okay, we have been posting live online lectures of all different subjects. So this was the completion of your first subject by me. Okay, there are other subjects also by me. This is the first subject that we have completed, my friend. Strength of material. A very big congratulations to all of us, my friend, for the completion of, for successful completion of this subject, strength of material. I had a very little time, I had a very less time. That's why I cannot guarantee that everything will be covered. But yes, all the major topics, all the major concepts we have covered, my friend, in this lecture series of strength of material, and I have tried to consider as many problems as I can. My friend, after the concepts end, I will also start a different lecture series for numericals. Okay, there will be a lecture series of numerical of SOM, there will be lecture series of numerical of MD, lecture series of numerical of mechanics. So there will be a lecture series for numericals also, different lecture series. This was the lecture series for concepts. Okay, in this lecture series, our basic aim was to understand the concept. Okay, in the lecture series of numerical, we will not discuss the concepts, we will directly solve the numericals. Okay, that we will start later. Okay, first we have to complete the concepts. Okay, so this was the completion of the first subject. A very big congratulations to all of us, my friend. You are also equally responsible for this completion. You are also equally part of this lecture, my friend, this series. So a very big congratulations to all of us, my friend. Thumbs up, hit the like button right now, my friend. And if you want me to make more and more videos, to make more and more topics, to incorporate more and more numericals. Please, my friends, support us by sharing these videos. Okay, we want these videos to reach to as many students as possible. If we are getting enough number of subscribers, if we are getting enough number of views, then we will be posting more and more videos. Okay, so please support us in our journey, in this journey, my friend. Okay, in this journey, please support us. We need your support. Please share these videos to all your friends. Post it in your Facebook. Send it to your WhatsApp groups. Okay, you must have WhatsApp group of your friends. Send it there. Send it to your friends personally. Ask them to watch these videos. At least send them. Watching or not watching, it's their decision. But your duty is to send them so that someone will get benefited. Okay, out of 100 people, maybe 90 people will not see, but at least 10 people will see. Those 10 people will get benefited. Okay, so your duty is to support us by sharing these videos, my friend. And if you keep on sharing, I promise you, we will be coming with exciting videos, exciting content, my friend. Okay, now my friend, I'm not saying that you cannot prepare for GATE or engineering services just by YouTube videos, but there is a limitation to YouTube videos. Okay, those of you who cannot afford to pay, you can obviously use these YouTube videos, and you have to work very hard and you will get succeed. Okay, but if you want to learn more, if you are able to pay, if you want to learn more, and if you want your learning to be a very sequential, a very structured, then my friend, please go and subscribe to Unacademy Plus. Unacademy Plus is India's largest online learning platform, my friend. All the big names in the industry of GATE and engineering services, all the top teachers of GATE and engineering services are teaching on Unacademy Plus, my friend. So you will have an opportunity to learn from all the top teachers of India, from Jammu Kashmir to Kanyakumari, from Rajasthan to West Bengal. All the top educators of India are on this platform teaching online live classes. Okay, and my friend, you only have to buy one subscription. Okay, you don't have to buy different subscription for different teachers, only one subscription, and you can watch videos of every teacher, my friend. Whoever is teaching for mechanical engineering, you can watch these videos. You can even watch civil engineering videos. You only have to buy one subscription. Okay, so one subscription and you can watch all the live lectures. What are the advantages of Unacademy Plus, my friend? You will have a direct conversation. You will have a direct mentorship. You can ask your doubts. There will be separate doubt sessions on Unacademy Plus. Okay, your entire syllabus will be completed in a very sequential manner, structured manner, like classroom. One subject is running, then one will end, second subject will run, then that will end, third subject will end. So your completion of subject will be very sequential, structured. Okay, so you will not have to worry which subject to read first, which subject to read later. So this will be the entire sequence. Okay, it will be in an entire sequence. There will be batch courses, means if you join a batch course, the entire syllabus will be completed in that batch. Okay, and my friend, you will get discount if you compare the cost of Unacademy Plus subscription with any classroom coaching. You will see that the cost is very less, very less, in fact negligible, my friend. 1 year subscription, 1 year subscription after discount, after 10% discount, you will get discount if you use my code. Okay, if you use my code, you will get discount. 1 year subscription will only be 22,500 rupees. Means, my friend, 60 rupees per day. 60 rupees per day. Only 60 rupees per day, my friend. And you can take the subscription. Okay, only 60 rupees per day. If you compare it with any classroom coaching, it is nothing, my friend. It is nothing. The amount of content you will get on Unacademy Plus, if you compare the cost, it is nothing. 22,500 rupees. And a very good news, my friend, you can pay on EMI also. There is EMI scheme on debit card and credit card. On debit card also there is EMI scheme. So you can pay this amount, 22,500 rupees in EMI also, using a debit card or a credit card. you have to use my code. Okay, you have to use my code for 10% discount. You have to use my code, which is Apuroop 10. Okay, there are amazing teachers on Unacademy Plus. You can watch all their videos if you use this code Apuroop 10. Okay, it is given in the description of this video also. Apuroop 10. If you use this code and buy the subscription, there is 1 month subscription, 3 month subscription, 6 month, 1 year, 2 year. I am just taking an example of 1 year because this will cost you very less. 1 year or 2 year subscription costs you very less. Okay.